Alright, here we're going to look at 5.5, cubic functions. Here's the why. Cubic functions show up when dealing with volume. Cube root functions allow us to look at the inverses of cube root functions. We ended 5.4 by looking at a square as it pertains to area and side length. We can do that same concept with volume. This page is going to be less involved than the square root page because there's actually less things happening. The notable thing that's nice about cube root functions is that both the range and the domain are all real numbers. So for cube root functions, anytime I have a cube root function, my domain and range are both all real numbers. And you can look at the graph and see why. This is going up and to the right forever. This is going down and to the left forever. It doesn't have a breaking point like square roots did. The reason that square roots had a stopping point is because whenever we needed to square root a negative number, we couldn't do that. It'd give us an error, and we're not going to be able to graph imaginary numbers. But with cube roots, you can cube root a negative number. Right? If I asked you the cube root of negative 8, even though it's negative, I can do that. It's negative 2. So that's good news. They do follow the same stretch compression, horizontal shift, vertical shift with up and down. The only thing that these guys will have special is something called an inflection point. The inflection point is going to be essentially the middle of this graph, and it's actually just your h and k value. So it's the same thing as a square root graph where we would track where did that guy start. It was h comma k. Cube root functions still have that h comma k function, except now that inflection point's where the other arm starts to begin. So it's still the starting point. It's the starting point for the arm that goes up and the arm that goes down. And finding the inflection point is very easy. It's h comma k. And they'll ask you this by saying, describe the key characteristics. We've already spent a lot of time with ending behavior, so we're not worried about the ending behavior on these, nor the domain and range, because they're both all real numbers. So the only thing that we'll have to check out is the inflection point. And all that is your h comma k value. Remember that h's are always opposite of what you'd expect. So 2 comma 1 will be the location for that inflection point. And when you plot that, you'll see, oh, okay, I see what that is now. It's where this arm now starts to go in that direction, that arm starts to go in that direction, with that inflection point being right in the middle. So that's the majority of the concept of graphing cube roots. Otherwise, things are exactly the same. Let's graph these by making a parent function and doing some shifts. I'm going to make us the most basic table, right? The parent function, y is equal to the cube root of x. And now we're going to be able to pick some negative values. I'm going to start with 0, though, because the cube root of 0 is 0. I can do both 1 and negative 1. Cube root of 1 is 1. Cube root of negative 1 is negative 1. But then we need to start picking values that are perfect cubes. And the next perfect cube is negative 8 and 8. So a lot of times you won't get very many of these points to show up on your graph unless you scale it. But this is the parent function. So I'm going to graph it in a highlighter here, color. So it'd start at 0, 0, go there and there, and it wouldn't quite make it up to 2 yet. So it's going to look a little bit like that, and this one's going to look a little bit like that. So that's the parent function. To graph y equals x cubed plus 1, understand that that's just a vertical shift by 1. So I'm going to take all these points, and they'll simply move up 1. So it's the exact same curve, except my inflection point moved up to 0, because there was no h values to move me left or right. 0, 1, which was that k value. So we just graphed that by understanding what's the most basic cubic function look like, highlighted in blue, and then we applied those shifts. Let's check this one out. I'm going to graph the parent function again. This is the most basic form, just like that. And we've got a couple shifts here. My inflection point is going to be moving based upon the h and k values. I need the opposite of the h, so positive 1, and then the k value. So this point here that was at the center, right now, it's no longer going to be at the center for our new equation. It's going to be at 1, 2. So we're essentially taking every point here highlighted in red and moving it to the right 1 and up 2. So if I move this guy, let's put a little blue highlight dot on. If we move him to the right 1, up 2, he'll look like that. The other point right here, right 1, up 2, lands it there, and then it would look like this. So it's the exact same shaped function, except all of it has been shifted right 1 and up 2 based upon our h and k values. You're also free to type these in on the calculator. To get the cube root on your calculator, you can hit math, and then option 4 within math is your cube root. So working with these, it's the exact same way as square roots or any other types of inverses. Whenever we graph the inverses, you'll see that we get the reflection line of y is equal to x. We can see that line happening right there. And we find the inverses just the same as always. By following the steps, you replace f of x with y, you swap x and y, and then you resolve for y. So this here's the original function. Here's its inverse, the inverse being denoted by that -1 right there. All right, so we're about to do a couple of these ones down here below, and we're going to get graphs that end up looking similar to this, to where they're reflected across the line y is equal to x. Let's start off with number 2. I'm going to go ahead and graph the cube root of, x cubed plus 2. It's going to look like this, and I'm just going to plug in the values. If I plug in 1, 1 cubed is 1 plus 2 is 3. If I plug in -1, it's -1 plus 2 is 1. 2 is going to go off the page, but -2 cubed is -8. -8 plus 2 is -6, so this one's also going to go off the page. He almost makes it there, though. And let's find the inverse by placing f of x with y, swapping x and y, and then solving, which I would do by subtracting 2 from both sides. Now taking the cube root, and then recognizing I do need to switch it back to the inverse of x. That way we can tell clearly that this guy here is the inverse of our original function. It would graph by starting our inflection point at 2, 0, right? Because of that h value and the no k value, he's going to start at 2, 0. And you can see the pattern from up above. It goes up 1 to the right, down 1 to the left, and then starts its curve like that. Starts this one's curve like that. And you can see that we get a curve, 2 curves, that are reflected across the line y is equal to x. That's how you know you graph 2 inverses correctly, when they're reflected across the line y is equal to x. Let's do one more that might be a little bit harder. let's take a look at one like number 1. I can graph this by plugging in points. Plugging in 0 gives me a value of 0. Plugging in 1 cubed is 1 times 1 is 3. The next one, negative 1 cubed, is negative 1 times 3 is negative 3. So this one's going to be growing very fast, right? Because that 3 is having it triple. And these might have a little bit more curve to them if you wanted to redraw them, because it's not a perfectly straight line. It does start to curve up quickly. To find its inverse, we replace f of x with y. We swap x and y. And then we start solving, which in this case will be dividing both sides by 3. So I've got 1/3 x is equal to y cubed. I can go through and cube root both sides to get that y is equal to the cube root of 1/3 x. Now recognize that I did not put the plus or minus sign because that only comes about from square roots. Cube roots can handle negatives on their own, so we don't have to worry about the plus or minus sign. Now, to graph this one would be a great candidate to type into your graphing calculator. It's going to be a little harder to do because we haven't studied what to do when there's a value with x. It causes something called a horizontal stretch. Another option you could do, though, is to understand it does start at 0, 0, and to understand that it's going to reflect across this diagonal line here. And if that's the case, you can almost trace these guys down and around to find out where the other point's going to land. And this is a little easier to do if I was to make my reflection line. If I draw it and take my time a little bit more, it's going to look like this. Here's my reflection line. You can then see that, oh, well, if this one's right there, that one's going to be right there. And if this one's right there, this one's going to be right there. By just drawing the reflection symmetry here. And that's another way of getting this one graphed, where that red line isn't a part of anything. It was just to help us understand that these are indeed inverses because they're reflected across that line. But there's our inverse. And you could have, if you went to your calculator and typed in y is equal to the cube root of 1/3 x, and you went to your second graph, you would have seen the points that we graphed, which were 0, 0, -3, -1, and 3, 1. Same ones that we graphed there in black up on our graph. Cube roots aren't going to be as prevalent for us in terms of how much time we spent studying square roots, because their domain and range isn't as interesting. As we noted, it's always all real numbers. The only thing that we have to track are those inflection points. So that's why we spent less time here on cube roots than we did with square roots, because it's more so just continuing on with looking at h and k and how that shifts our graph left and right and up and down.